I destroyed one of the keys on my keyboard. The Y key is actually not working properly, so I had to order a replacement keyboard from eBay this morning. But it's going to be an improvement. The new keyboard is actually backlit. Like all those gaming keyboards, where it's backlit. Yeah.
It helps so much.
Especially your fingers covering the key that you're supposed to be hitting, right? Yeah. So anyway, this is your homework assignment. So the homework assignment is called CNF. We'll talk about CNF in a little bit in today's lecture. CNF stands for conjunctive normal form. Okay, so no need to write it down because we will be talking about this pretty much the entire class today. But the idea is any logical expression, like this one, can be converted into conjunctive normal form. And that's basically your homework assignment. Your homework assignment is to turn this expression into a conjunctive normal form. All right? Okay. So I just want to introduce a homework assignment first, and then we can go back and talk about, okay, so what is CNF and how do we convert it? So that's what we're going to talk about next. And if you remember from last Wednesday's discussion, the way that a propositional logic space or WFF space is constructed is it has an infinite size, which is a problem because when your WFF space is infinite, then looking for a particular WFF from your iota set of iota is going to be an issue because how do you know that you're going in the wrong direction? How do you know that the expression that you're interested in is actually not a theorem? Instead, you will never reach it. As opposed to, it is a theorem, but we haven't reached it yet. Do you understand what I'm talking about? In other words, I want you to find a needle in a haystack. Okay? So here's an infinite haystack that I want you to find a needle. But the problem is the needle may or may not be there. So when do you call it quits and say, okay, the needle is not in the haystack, as opposed to, yeah, I know it's in the haystack, but I haven't found it yet. How do you determine whether, one way or another?
Get a metal detector.
But remember, your metal detector only has a finite range, but the haystack itself is infinitely large. Yep.
That's why you get infinite metal detectors.
Yes. Magical infinite metal detector. Yep.
You have a magical haystack.
Would you have to decide whether or not it was even possible for the needle to be in the haystack?
Well, you don't know until you try. That is the problem.
Well, yeah, but you decide before even searching. Just
Like, do we see it fall in there?
yeah. So is it reasonable to assume the needle is in there?
No. Because you're asked to prove a theorem, but nobody tells you that the theorem itself is actually true. So you have to find out whether it is true, and if it is true, how do you get there? So go back there and then here. Yep.
So that you can reduce the initial statement, or somehow transform the initial statement into something that is contradictory that doesn't make sense.
But it still has an infinite space to search or infinite space to explore before you can find a contradiction. So proof by contradiction doesn't help in a case when your space is infinitely large.
From just one statement. What's the context if it's just one?
You have one WFF one formula that you're interested in, and you say, okay, I want to know whether this quote unquote follows whatever is known to be true in iota. That is your question. Okay, I want to know whether this is true or not. Whether it follows from everything that is known to be true in iota. Using the transformation rules, which is also called inferences, that is given to you in zeta. Okay? And if your space is infinitely large, then it's really difficult to come to that conclusion. And yes, go ahead. You can, okay, so you can prove a theorem is false by using counterexamples. But if your interest is to know whether the theorem is true or not, then you don't even know whether it's true or false to begin with.
Well, can you just start out? Would it be easier to just start out with tries to false?
By assuming it is false?
No, but trying to.
By trying to prove that,
It's false.
then you end up with the same problem, because now you just negate the theorem that you wanted to prove to be true, and then you're trying to prove the negation of that to be true, right? So you end up with the same problem. There was another hand. Yep.
You could narrow your search to where you think the needle's going to be.
Sorry, say that one more time.
You can narrow your search to where you think the needle's going to be.
Then how do you know where to search? Remember, your space is infinitely large. Okay.
I think it's easier to just decide, just guess.
Yeah.
It's either in the haystack or it's not
The
in the haystack.
the question is, when do you call it? When do you make a conclusion? When you find it, exactly. Okay, when you find it, but when do you make a conclusion when you cannot find it? So okay, so let's say I tell you guys that I lost my stylus, which I did, okay, somewhere on this campus, okay, and I'm telling you, okay, either you can prove, you can come home, after you can either prove that I did not drop my stylus somewhere on campus, like maybe I lost it at home, okay, or you actually find it. Until then, don't come back to me. That is, and this campus is actually finite, right? I mean, it would take a lot of time to exhaustively search every single place on this campus, but it is still finite. So now, when you think about this space being infinite, how do you make a decision? How do you say that, Tech, maybe you left it at home, but I don't want to know whether it's possible that I left it at home. I want you to prove without a single doubt that yes, you left it at home, or here it is, we found it. And buying another one from Amazon is not an option. Yes.
Well, in this example, you can always follow, retrace the steps you took. That already narrows it down.
Yes. So that becomes a smaller space, which makes it easier to deal with. So, but that's the whole point of resolution. Okay, so we are basically moving on, and oh, by the way, I found the proper word of this particular symbol. I said what did I say? Entail. It is incorrect. It is infer. So a transformation is also known as an inference. Okay, so the symbol by itself is called infer. So all of these phi's, as a set, infers in this case psi. So there we go. So we are jumping on to resolution, and then we'll go back and talk about soundness and something. But I want you guys to do something, for homework assignments. Okay, so resolution is interesting. So in order to understand resolution, we'll take a look at this implication here. So when you look at this expression, it is nothing more than another well-formed formula, right? Okay, it has got disjunction, conjunction, negation, implication, and it is syntactically correct. Are we buying that? Okay. So everything that has two operands, in fact, has two values to work on. Everything that only has one operand only has one thing to work on. So it is syntactically correct. So now I want to see how far this can get. Okay, I want to see. Okay, how far can we get with this one? Okay. Now remember, this is the entire expression that I'm interested in. I'm not only interested in the first part, to the left of the implication. I'm not only interested on the one that is just to the right hand side. I'm interested in the implication itself. Okay. So on the first line, can someone tell me what I did to transform or to turn it from here into here? Is the definition of implication. Okay, A implies B is not A or B. Okay, so I negate everything to the left hand side, and then I say or everything that is to the right hand side. Is that okay? So that's why we have the negation on the outside, and the pair of parentheses includes everything that was originally to the left hand side of the implication. Yes.
So if you're, I guess, negating the left side of the disjunction, then the right side would get that extra parentheses just so you kind of keep track of
Yeah, just as an extra emphasis. Yep. So this extra pair is not really needed, but I put it there because to emphasize that we are applying the definition of implication. Okay, what about the next line? How did I go from the first line to the next line? What did I do? Something really, really kind of, well, I did two things. Okay, they're parallel, but they're not, it's okay because each one is only one step from the line before. What did I do to the left-hand side of the overall conjunction? In other words, what did I do to this part here? I distributed negation, which is also known as De Morgan's law. Okay, so De Morgan's law says, I can distribute, quote unquote, distribute the negation to the inside. So now I end up with the negation of the first part of the conjunction, this conjunction, and the negation of the second part of the same conjunction. But I have to change the conjunction into a disjunction in the application of De Morgan's law. What did I do to the right-hand side of the overall disjunction? Yeah, I just got rid of the parentheses because of the associative law. Okay, whether the parentheses are there or not does not really matter. Question?
Yeah, about the Morgan's law.
Yeah.
Did you switch the conjunction to
Yes.
is that just what you do?
Huh?
Is that what you're supposed to do?
Yes. The Morgan's law requires that you change. If you start with a conjunction, it becomes a disjunction. If you start with a disjunction, it becomes a conjunction. Okay, so let's take a little pause here, and we'll talk about the De Morgan's law. Okay, it's kind of important that you understand these tricks and understand why they work. Okay, be able to prove that they work. Okay, so we'll go ahead and start with variables x, y being independent variables. So we have not x and y, and then we have not x as one thing. Okay, let me use parentheses here. Not x or not y. Okay. X, y being independent variables means that we can do x 0, 0, 0, 1, 1, 0, and 1, 1. Those are the only four ways you can arrange values of x and y. Okay, so what should go here? This is a NAND, otherwise known as a NAND. A negated AND. That's a 1. Okay, cool. What about this one? It's going to be a 1, because if at least one side of the conjunction is a 0, the whole conjunction is a 0. But I have a negation on the outside, so if the conjunction is 0, then the overall expression is a 1. So we got 1, 1, 1, 0, basically. Ah. Now, how did I do that? Nah, I just pasted, I think. Okay. So 1, 1, 1, 0 for this one. And what about this column here? Okay, x is a 0, y is a 0, right? So not x is a 1, not y is a 1, 1 or 1 is definitely 1, okay? And on the next row is pretty easy to figure out as well, because at least one side is a 1, so the whole thing is a 1. This one applies the same way as well, but on the last row, x and y both being 1s means that the negation of each one is a 0. So we have 0 or 0, which means it is 0. Is that okay? I'm going to leave the actual detail, the mechanical part of working out the cells to you guys, because you can do this with a spreadsheet. Okay? There's no need to actually use brain juice to do this. You can use a spreadsheet to do it. So the significant portion is when you look at this row and in this column, and look at this column, what do you notice about those two columns? They are identical. Okay. In Boolean algebra, this is just as good as any other proof to show that two expressions are equivalent. Okay? Cannot use this trick in integer arithmetics, but you can definitely do it with linear algebra. Okay? So that's the first one, and there's another one. I'm not going to do this, but I'll leave it up to you guys to convince yourself that they are equivalent. Okay, so I'm going to give you the format, but you get to prove it. Okay? This is what I want you to work on if you have time. Just work it out the same way that I did before, and convince yourself that the negation of a or can be re-expressed by distributing the negation to the inside, but changing the disjunction to a conjunction. Is that okay? So I'm not going to show you the proof, but you can definitely work on this yourselves and convince yourself that, yep, they are in fact the same. In fact, if you have time, I would challenge you guys to do this proof using Google Sheets. Google Sheets actually understand logic. It has and, it has or, it has not, and you can use true and false values in different columns, and you can definitely tell whether they are the same or not. Okay, so this is the detail of De Morgan's law. So getting back to the application of De Morgan's law. So getting back to the application of De Morgan's law, this is how I applied De Morgan's law, is to turn this into this. In other words, I distribute the negation, this negation here, into the components of the conjunction, but then I have to change the conjunction into a disjunction. Is that okay? All right. How did I go from the second row to the third row? What did I do? De Morgan's law again, but this time it's the other De Morgan's law, because I am distributing a negation into the inside of a disjunction, so the disjunction becomes a conjunction, and the negation now applies to the individual components. I kind of skipped one step here because of the double negation becomes just psi. So that's one extra step that I should have shown, is double negation cancels out. What about from the third row to the fourth row? That seems kind of silly, isn't it?
That's confusing. Is that or one?
Huh?
It's and one.
It's and.
But one's always true, so you just
One is true. One is the constant of being true. So, so how do I go from phi to phi and true? How do I go from row to row and true?
because it's always dependent on the phi, so it's still
It's just an
it's like
identity.
adding zero.
It's the identity, exactly. I like that word.
It's
Okay.
like p times 1 or
So
something.
true is the identity of the conjunction operator, and then 0 is the identity of disjunction. Okay. But I just made a baseless claim, or you guys are supposed to say that. Tech, prove it, right? So how do we prove something like that? In other words, how do we prove that this expression is exactly the same thing as this
You
expression?
can do a table even.
You can do a table again. Exactly. This is the one thing about Boolean algebra that is really cool, is you can almost do everything by a table. Okay. Okay. So we'll do this really simple table because we're talking about one single variable in this case. So if x is 0, what happens to x and 1?
0,
Okay. If x is 1, what happens to x and 1?
1.
Okay. Well, do we see the two columns being the same? Proof is done. It really is, quote unquote, as simple as that. Okay, is to use a truth table. Okay, cool. So when I did something like this, I'm doing it so that I can turn this 1 into something even sillier, right? I mean, I'm making this longer and more complex than it needs to be, right? And then this one here is also getting longer and more complex than it needs to be. But can we prove this? Can we prove that true is the same thing as any Boolean variable or the negation of itself?
It's like x.
It makes sense, right? But can we prove it?
Yeah, same way.
Yep. So over here we say this is x, this is x or not x. Okay, x can be 0 or 1 because it's a Boolean variable. If x is a 0, what happens to x or not x? Not x is a 1, so the whole disjunction is 1. When x is 1, then obviously x itself is a 1, so the whole disjunction is also a 1. So now we have proved that doesn't matter what x is. If x is a Boolean variable, then the disjunction of x and its negation is always guaranteed to be true. So is that okay? All right. So that's why we can just turn this one into something complex like that. And then from here to here is distribution. So I'm just distributing this into here, and I'm distributing this into these two. Which symbol?
What you just said, x and not x, but like in this example, the two symbols. that
Oh,
you
why we
used.
use psi?
Yeah, why was it particularly psi and not some else?
Because later on I can combine the size with other things, and cancel things out.
Okay, so you did it with like an actual.
When an
plan.
intent, yes. So there's a particular intention to do it. Yep.
And so, like, how do you intuitively know to do that like, ahead of time without knowing? Like, if you're just solving this out, as
That's a good question.
you just
I can guarantee that this is actually my proof. I didn't read this proof from somewhere else.
you just play around kind of.
Yeah.
I think at some point, I look at what I have on this side, and I look at what I have on this side, and I go like, I do have, psi and not psi over here. So the symbol psi has significance because it is the one thing that is quote unquote common between these two, even though one is negated and the other one is not. So, but on this side we have nothing that has psi. So there's nothing that can help me quote unquote cancel out psi on the other side. And that's why we go like, maybe we can just introduce psi somehow into these expressions. And the quickest and easiest way to introduce a symbol in Boolean algebra is to say, oh, okay, we can always add 1, okay? Or, in the case of OR, you can always OR 0. In the case of ORing a 0, you can say it is psi and not psi, because that's guaranteed to be a 0. So, but that's how you can, out of nowhere, just magically, make a symbol happen. And then once we do the distribution, we end up with something that's longer. But now we have psi and not psi, in this whole thing, and hopefully these things will help us, do the canceling on the other side.
So you kind of have like an idea or like a rough prediction of what you want it to do, and you like
Yes.
plug it in, and you hope that like.
I do know that this is what I want.
Right.
Okay? But in order to get here, psi becomes important because phi and rho are unrelated, completely unrelated. So I cannot rely on those two to give me truth. Okay? Psi is the only one that is kind of in between these two. So that tells me intuitively that I need to introduce psi on the other side in order to hopefully get to a cancellation of some kind to give me a truth. The value of truth. Is that making any sense? So I can only describe like post-rationalization of my thinking process, but I'm not sure how well that's going to be helpful. As I said, it's post-rationalization, which means exactly what went on in my head at that time, I cannot tell you. I want to tell you, but it's not something that I actually have access to. It's like having a program to describe itself, right?
You need an interpreter.
Or a neural net to read my neural net.
Yes.
Okay, so we ended up with this long, huge expression, but the nice thing about this long, huge expression is I can cancel things out. In other words, I can look at this and I go like, we can group things. Look at this here. This has the negation of phi, and it has a conjunction with the negation of psi. And then over here we have this guy here, which has phi, but it also has the negation of phi. So I decide to pull these two. Okay, I decide to pull these two together so that I basically do factoring, which is the reverse of distribution. Okay, and I do the same thing with the row term. Okay, so I look at this one. Okay, that's kind of cool. And then I look at the other term, which is, where's the other one? Oh, down here. Yep, so I look at this one, and I pull those two together into this one. And then the rest, I just kind of, the leftover terms are just the leftover terms. So now we have this, okay? Okay, is everybody convinced that the negation of phi or phi is just simplified to true? Okay, we just proved it a little bit earlier. And then the same thing over here. And then we have these two leftover terms, which we will never use these two leftover terms, because once we simplify this to just the negation of psi, and we simplify this term to just psi by itself. Now we have psi or not psi on the outside. So we got a 1. Well, 1 or whatever is always a 1. Is that okay? So so the trickiest of all the steps is the introduction of psi when it didn't exist on the other side. That would be the trickiest part of this entire proof. Okay? All right, so we just look at the pine needles. So now we need to take a step back at the pine tree.
So this is what we're gonna be doing for the homework, right?
Nope.
Oh.
Nope. Your homework is a little bit easier.
Okay. Thank God.
Okay, I'm just trying to make the screen look.
But this is
Oh, okay. I scrolled. That's why.
Would you expect to do something like this in the exam?
No. No. I put this into the notes. I could have just said that the whole thing is true, right? I could have just, I could have just said that this is always true. Could have just said that, right? But I need to convince myself. So since I went through the whole process to convince myself, I might as well just put it here so that you guys have some exposure to how to prove something like this. Yep.
And you're saying this is resolution.
This is called resolution. So the bottom line is, this implication is always true. What does it mean when an implication is always true? So you look at the definition of the implication, right? So let's look at the definition of an implication again. So we got x, we got y, we got x implies y. That's implication. So we just look at this whole thing again, which most of you really should know now, because we have a lot of things that rely on this. Okay. This is the only time when the implication itself is false. Okay, so that's the truth table of implication. And we know that particular implication that we just looked at is always true. In other words, we know that the third row of this truth table does not apply because the implication is always true. So the only three cases we have to think about is, oh, maybe x is false. Well, when x is false, we don't really care. Okay? But the other thing is, if x is true, y has to be true. That is the whole point of that implication, is when x is true, y has to be true. So getting back to the slide, what it means is if you know that these two expressions are true, this one has got to be true. What if one of those things on the left-hand side is not true? We don't care. Okay, that's not our concern. Our concern is if the conjunction is true, then the right-hand side of the implication has to be true. Is that okay? What is the significance? What do you think is the significance of this particular implication being always true? When you look at the left-hand side, we have 3 independent variables. When you look at the right-hand side, we only have 2.
One of the variables.
Got it. Just disappear. Yep.
Is this a little bit like transition relation?
Transformation?
Transitive, sorry.
No, it is not transitive. Okay, so do not look at this as transitive.
But kind of like the same thing.
No, it is not. No, ignore anything that you remember from being transitive. This has nothing to do with being transitive.
But if you want to prove that it's transitive, like
No, it is not.
not this case.
Because you need a negation on the second one. So you need one expression to have psi, and the other expression to have the exact negation of psi itself. Okay, the rest we can concatenate. So if you can look at psi and not psi kind of as like an interface that you can plug in. So it's plugging phi with rho. But when you plug it in, this term disappears. It is gone. Okay? But the significance is we got rid of one independent variable when we do this transformation. Is that okay? So in resolution, what we're doing is we're turning this implication into an inference. We just write an inverted t or rotated t in place of this. It becomes a transformation rule or a syntactic transformation. It's completely mechanical. Okay. So that's one important piece in the homework assignment. Well, not with the current one, but with the next one. So with this, we also have to make some changes to what qualifies as a well-formed formula. Okay, so you can see how I'm turning that implication into an inference. Okay, if you can find me something like this, and find me something like this, then we can infer that. Okay, it becomes a completely syntactical, type of transformation that does not depend on meaning. But in order to do this in a much more efficient and mechanical way, we kind of have to redefine how we express well-formed formulae. So we limit ourselves to omega 1 being just negation, but that's kind of like the same way before. We only have one unitary operator in Boolean algebra. But this part is interesting because before we had a whole bunch of operators that require two operands. Okay, we got conjunction, we got disjunction, we got implication, we got equivalent to, or if and only if. Now we say we only need or. Disjunction is the only one we need. That's an interesting change. And then the next part, I thought I made changes to this already. Why is it not getting changed? Oh, I know why. Let me see if a refresh will change this. Okay. Yep, okay. So let me go back to this one. Okay. So this is after my modification. It took a while for MathJax to update the screen because it needs to re-render everything. Okay, so instead of using the confusing term of is a well-formed formula 1, okay, which most people would think of cars immediately. Okay, you guys are not getting it.
Well, Formula One.
Well, because in the United States, people only know NASCAR, right?
I don't think.
The cars are really fast, but they only make a left turn. They're always making the left turn.
I feel like this region, not so much.
That cat's going in a circle so much better than that other guy.
But in Formula One, you kind of have to. It can make you dizzy just watching the race. Can make you dizzy. It's like left, right. U-turn, hairpin.
No, little giants.
Okay, so I'm using the other term here is a disjunction element. Okay, that's what DE stands for, disjunction element. Okay, so we want to say, okay, what is a disjunction element? Anything you find in alpha can make a disjunction element. Is that okay? What about the negation of anything that you can find in alpha? Same thing. Okay, so if P, Q, and R are in alpha, then P is a disjunctive element. Disjunction element. Q is a disjunction element. So are the negations. Okay, not P itself is also a disjunction element, which means it can be in a disjunction. Not Q, same thing, and so on and so forth. Is that okay? But we are limiting to only things that we can find in alpha. In other words, E itself cannot be another DE. Cannot be another disjunctive element. E can only be one of the things we can find in alpha. Is that okay? So this is one level of rule that does not exist in the quote-unquote normal propositional logic. Okay, we are imposing a hierarchy here. Okay, so now that we have defined what is a disjunction element, then we look at this and go like, okay, I will give you n disjunctive elements, okay? Because I'm saying that I is from 1 to n, and phi I, phi 1 all the way up to phi n are disjunction elements, okay? I'm confirming they're already disjunction elements. If that is true, then the disjunction of all those terms is well formed. I mean, okay so far with this notation. So what is well formed? A well formed formula becomes It can only be a disjunction, okay? But inside the disjunction, it can have individual things they can find in alpha or the negation thereof. Is that okay? Don't you think this is a lot more restrictive compared to what we had earlier, where you can have negation, conjunction, disjunction, implication, equivalent to, and a well-formed formula is basically recursive. This is not recursive at all. This definition of what is well-formed is not recursive. It is definitely structured, single level. Is that okay? And I'm making a claim that this system can express exactly the same kind of expression as you can express in general as Boolean expressions. That is a pretty big claim, right? So how do we make this happen? Okay? And what is an example of this? Oh, by the way, I also made some changes in my notes. I haven't really propagated this change to all the notes yet, but I have a table of contents. So this way, if I have a long module, this one is a little bit long, you can just basically go click on a particular item and we can get there. So if we are talking about resolution, we just jump to resolution. So that's kind of cool. It makes it easier to navigate. All right. So now we want to know, how it is complete. In other words, can every general Boolean expression be re-expressed in this particular form? The first question is, where's conjunction? Conjunction is actually not needed, because when you are using inference, anything that can be inferred is automatically in a conjunction with everything else that can be inferred or in iota itself. Let me say that one more time. Remember the picture that I drew in the previous class, the entire WFF space? Okay. Iota represents everything that is red to begin with. Okay. If you can say, oh, here's a dot that it was not originally labeled red, okay, but I found an inference. Okay, I found an inference that can take these two things from the iota, and it can be inferred. Well, guess what? That is now labeled red. But everything that is labeled red are in a big, huge conjunction. They're all components inside a gigantic conjunction. Is that okay? In other words, what we're really saying is everything in the iota are true at the same time. It is one conjunction to begin with. But if you can use rules of inference to infer something else from things that are already known to be true, that would be true as well. But it is related to everything else using a conjunction, because it is also true when everything else that is labeled red is true. Are there?
Can you change the iota and change everything else?
You can change the iota and you can change how things are labeled. That is correct. Yep.
So I was going to ask, when that becomes red, then is it considered part of iota?
No, it is not a part of iota because you didn't start with this one. So iota is still finite and fixed. But you can kind of imagine that, the dots that should be labeled red is already quote unquote labeled. Okay? But how do you know which one is red and which one is not requires the use of inferencing. So are we clear on why conjunction is not necessary in this case? Okay, all right. So now we want to know, okay, why is this complete? If we are given something that is not well-formed according to these new rules, what do we do to make it well-formed? That is the question. Okay. So let me see right here. Okay, so if you have something that is like this, okay, we are always given that phi is well-formed and psi is already well-formed. Or no, I take it back. Sorry, excuse me. We're given that we have two general expressions. They may not be well-formed in the sense of their disjunctions. Okay. So I'm saying that if phi is already well-formed and psi is already well-formed, then the disjunction of these two is well formed as well. Can you guys buy that? In other words, if I can tell you that phi is a huge disjunction of some terms and each term is either something from alpha or the negation thereof, okay, and that's why it's well formed. And psi is the same way, okay, psi is one huge disjunction where every single component of that disjunction is either something directly from alpha or the negation thereof. And I make an even bigger disjunction of those two. That disjunction would also have the correct properties to be well formed.
Oh, so you're checking just to make sure the parts individually.
Yes. Yeah, exactly. If they're individually well formed, then the disjunction of those two would be well formed as well. Can we buy that? Okay, cool. What if we're given a conjunction? Oh, okay, note the otherwise. Otherwise, apply the other rules. In other words, if at least one of phi or psi is not well formed, apply the rest of the rules. Okay, so let's take a look at the rest of the rules. One rule is basically saying, what if we have a conjunction? Well, if the top level operator is a conjunction, that's easy. All you have to do is to consider phi and psi separately. Because remember, anything that is in a conjunction, you just split and go like, yep, you're on your own, and then we treat each one individually using the same rules. It's kind of recursive. Is that okay? I can show you, how this all works out in an example later on. Okay. What if we have an OR? We have a conjunction on one side, and then we have a disjunction on the outside. Then we just apply distribution. Okay, we apply distribution, which will basically turn these into two different things. One term is going to be phi or rho. The other one is going to be psi or rho, and then each one of these will go back to the first step to be analyzed. So once again, it is a recursive way of looking at things. Is that okay? Yep.
The word "and" there is conjunction, right?
Which one?
Where it's phi, disjunction, rho, and. That is the conjunction.
We have these two. Basically, we have these two terms from the distribution of this.
Right.
So these two are connected by a conjunction, yes.
Yeah. Okay.
But because they're connected by a conjunction, that means, this we can consider on its own, we process it on its own. And with this one, we can separate on the other side and process that on its own as well.
Right.
Okay? What if we have a negation on the outside? What if the topmost operation is a negation? Well, if the topmost part is a negation, then it has to be negating either or negating an and. So the only thing you can do in that case is to apply the Morgan's law. Okay, move the distribution into the inside of the operation. And then whatever is the result of applying the Morgan's law, go back to the first step and process that one. So this is going to be recursively, working on things until you have, completely just disjunctions left. Is that okay? Are you guys convinced that this can work on any legitimate Boolean expression and turn it into just, conjunctions of big disjunctions? Maybe.
Yes.
Okay. So I kind of look at it in a slightly different way, as operators and whatnot. But let's not read this, okay? Instead, we'll look at an example. So we'll look at this thing, okay? Does this look like a normal Boolean expression? Not well formed anymore according to our new rules, but is it a legitimate Boolean expression? It looks okay to me. Every negation only has one thing to work on. Disjunction has two things, implication has two things, disjunction has two things, and conjunction also has two things. So it is legitimate, okay? Structurally speaking, this Boolean expression is okay. But how do we turn it into a gigantic conjunction where each component is a disjunction? So we start with this, and then you can work on it in a in different ways. Okay, so the way I work on this is I first apply the definition of implication. Okay, so let me scroll up a little bit here. So R implies Q becomes not R or Q. Okay, and then I apply De Morgan's law to this one. So the negation of R is on one side, the negation of Q is on the other side, but when you apply De Morgan's law, you have to change the operator, so OR becomes AND in this case. And from here to here, it's just a simplification. Double negation cancels out, as if it is not, it's the same thing as not having negation at all. And then from here to here, I'm using distribution. So we have this entire thing as one single expression distributed by conjunction over a disjunction. So now we have R and not Q and P, or R and not Q and T. Are we still doing okay so far with this step? You basically just look at R and not Q as one thing. Okay, so this becomes one thing, and then you have an AND, and then the other side has an OR, so now we can use distribution. Are we still doing okay? All right. Okay. And then from here to here is another distribution. So this time we are distributing this entire expression over that entire expression. So we have 9 components. Okay, so we got R and R. This basically it's just crossing everything. It's kind of like a Cartesian product basically. So you have RR, you have R not Q, RT, and then you have not Q, not Q, not QT, and then we have PR, P not Q, and then PT. So that's how we have a pretty long expression like that. And then we decide to distribute this not P through the OR to this entire conjunction. So now we have this entire thing, and this entire thing, and the entire thing, and so on. So it becomes rather long, right? Well, the good thing is we can simplify. The way we can simplify is we look at this, we go like, hey, that's just 1. Okay, but 1 or whatever is just 1, so that's why this entire expression simplifies to true. Same thing applies here. We have not P or P, so that simplifies to just true here. This one has not P or P as well, so that also simplifies to true. So are we doing okay so far with that simplification? But then we also did some other simplifications. The other simplification that we did has to do with P or not Q. Okay. Okay, first of all, are we convinced that this is just that? How do we prove that? How do we prove that for any Boolean variable, x or x is the same thing as x itself? The truth table, exactly. Okay, I'm not going to show you that truth table, okay, because that would be absolutely boring. Okay, cool. So we can apply that here, and we can also apply the same thing over here, right? Not P or Q, not Q or not Q. The not Q or not Q simplifies just to one single not Q. Is that okay? Okay. But then the next step looks kind of strange from here to here. Okay, from the second last step to the last step, that looks kind of weird because what happened to not P or R or not Q? It was there before, now it's gone. How did that go away? And then we have this, not P or R or not P or T. That's gone too. And then we have this one, not P or not Q or R. That is gone as well. How can they be gone? Huh? There are 2 ways to prove that. You can use a truth table, okay? You can also use Boolean algebra to prove it, okay? So let me show you what I'm trying to prove here, okay? So the idea is when you have 3 variables, x, y, and z, okay? They're independent variables. If you have x or y, okay, as 1, and then the other one is x or y or z, okay, I'm claiming that x or y or z is really the same thing as just x or y. Is that okay? So how do we prove that? Now, truth table is the first way to do it. It is completely unnecessary in this case because you can actually just use Boolean algebra to do it. But if you want to do it this way, that's fine. Just takes a little bit longer because the table has 8 entries, where these are all 1s. Okay, so we look at x or y here. Okay, we know the OR truth table, right? So this would be 0. This would be 0. Nope, that's not true. Okay. They're not the same, but one implies the other one. Okay, I think the implication goes here. Okay. So they're not the same, but but that's the implication. So now we have a 1, another 1, and all of these are 1s, right? Because x is 1, so anything that involves x is 1. Okay. Are we okay with the first column, which is just a regular OR? Okay. Now with the second column, this is the only row that has a 0, because everything else has at least one variable having a 1, so they'll be all 1s. Are we convinced about this? How the two tables work out? So I was incorrect when I said they are the same, but they are not. They are not the same. But we can still establish that x or y implies x or y or z. Is that okay?
Yep.
Well, if that is the case, that means x or y or z is not really needed. If we already know that x or y is true, we don't need to specify x or y or z, because that has to be true.
See, so wherever not P or R repeats or is common,
Right, because if not P or Y, excuse me, in order for the entire conjunction to be true, every single individual component has to be true, right? But if not P or R is one component already, and that has to be true for the entire thing to be true, guess what? Everything that has not P or R or blah 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 also has to be true. But that's not needed because if this is true, the other one has got to be true. We don't have to write it. So that's how we can go from the second last row to the very last row in this particular proof. It's because of this implication. Yep.
And with this, since they're all in conjunction, all these statements, then that's ideal.
So that's why this is called a conjunctive normal form, because in the actual representation, you only have this as a well-formed formula, and then you only have this as a well-formed formula, individually existing, but they are implicitly connected by a conjunction. So this conjunction here is implicit. But when we write it out in a proof like this in the derivation, then the conjunction is explicitly stated. You can always replace the conjunction symbol with a comma. Then you just basically end up with a list of expressions that are inside a big conjunction. Is that okay? All right. Cool. So now when we look at the homework, where's the homework? There we go. So when we look at this, what do you think? It might be a little ugly, but do you know what to do with it?
We can handwrite it. Right?
You can. There's an area for you to turn it in. So when you turn it in, there's an editor box, like an HTML editor box that you can use to enter your answer. When you say handwrite, do you mean hand type? Or do you mean handwrite and then scan it?
That's cute.
No, you have to you have to type it. I suppose since it is an HTML editor, you can have that to refer to an IMG element where it is your actual scan.
So, do you want the full expansion of it you said, or
Yes.
okay.
I want a full expansion. You can carry out multiple steps in different parts of the same expression. So that can happen. But of the same part, I don't want you to skip steps. Except for the double negation thing, which I do a lot. Skipping the double negation. Is that okay? I personally would just use the built-in HTML editor. Let me just kind of change the instruction or add to the instruction a little bit to make it easier so that you guys can just type it instead of using the equation editor.
See you next Wednesday, right?
It is due next Monday.
Oh.
You got 1 week to do it. 184 hours minus 1.
You have 6 days to procrastinate.
Huh? Oh, for some people, yes. Okay, and you can use any logic notation that we have discussed. Okay, so that means you can use this for or not, multiplication. Okay, for and then plus for or. Okay, I think we talked about that in this class. Did we talk about that?
Beginning.
Okay, so you can use that, and multiplication can be implied. So if you have P and Q, you can just say PQ. That makes it easier to type. So would that help?
Yeah.
Yep. Okay. I'll give you an example in each one. So
Can we just have like two variables with each other to find this and, or do you
yes, that's what I just said. Yep. Let me. This editor cannot keep up with my typing, and it doesn't buffer, which is a problem because I can type faster, and then it just loses my keystrokes. Huh?
How does it not buffer?
Because it's dumb. Okay. Okay, is that okay? I'm just giving you guys examples, just in case you guys want to have a reminder of this. Okay, X. See, I can type way faster than that, and it is having problem keeping up. Okay. Okay, X dash. Oh, this is V. See, it just cannot keep up.
Maybe you switch view.
Hmm?
Maybe you switch view to this. What does that do?
That won't help. The problem is it's trying to refresh the rendering all the time, and it doesn't buffer the key. If it buffers the key, it's okay, but it doesn't buffer,
You type it somewhere else and copy paste it.
Huh?
Type it somewhere else and copy paste it.
That is possible. I'm not sure whether that will work or not. You can experiment. But now that you can do this, you don't have to use the equation editor, right? The whole point of using these alternative symbols is that you don't need to use the equation editor. Because everything, the exclamation point, the times, and the plus, they're all on the regular keyboard. But use extra parentheses to make sure that I understand the order of operation. Without parentheses, I would use the same usual arithmetic operator precedence, which means negation applies first, and then multiplication, and then addition or disjunction has the least priority. Is that okay? Okay, so I'm gonna say this. Mm-hmm.
Is there an issue if we put too many parentheses in, that it does not make it incorrect?
It depends on in what way it is too many. If you have too many open, then I cannot tell how it is closed. Right. If you have too many closes, then it's okay. I would just ignore the ones that that have nothing to match to. But if you have too many opens, then it becomes an any issue. Is that okay so far? Do you guys know what to do with this homework assignment? Okay, all right.
No, you should
All right. So when that is okay, we're going to go back to the discussion of completeness and soundness. Okay. So when we look at this, okay, using this infer symbol, we are only specifying a syntactic operation to basically say it's a pattern matching. Okay, we specify phi 1 all the way up to phi n as patterns. If that pattern matches at the same time, then we can transform, okay, syntactically transform all the things that we extract out of the phi 1 and phi n into psi, which is another expression that has conjunction, disjunction, and all kinds of stuff like that. But this symbol means it is a syntactic operation. It is not based on meaning. It is simply saying, okay, pattern match, and that's the result. Okay? Are we doing okay so far with this? Okay. Another way to put this is if positions is not important, I can probably code this in regular expression matching. Okay, that's one way to put it. When we use this symbol, implication, we are actually referring to the meaning of all of those things. Okay? And I think I use the wrong symbol here. This should be a conjunction, not a disjunction. Let me fix that first, because I hate to have the wrong symbol used here. This should be a conjunction, not a disjunction. So let me fix that. Let's see. I'm just looking for the words Boolean algebra in uppercase B. There are too many Boolean expressions. I should look for completeness. There we go. Okay, got it. And then we're looking for big V. The big V should be the reverse of V, which is, I cannot remember. Big wedge. Okay. It only makes sense that it's big wedge, because the without the big, it is just a wedge. Okay. Okay. Yep. There we go. Now we have a big wedge. No, it's still reformatting. It will finish formatting in just a little bit. There we go. Yay. Okay, so semantic entailment is expressed as this. So when we have semantic entailment, it means that if we have a rule like this, then we can prove using actual Boolean logic that the conjunction of all of these sides actually implies the side which is the result of the inference. So the direction of the if then is, if we have this inference, we should be able to prove that the inference makes sense.
Oh, so that's what it means?
That's what semantic entailment means. It means you're...
And that's the symbol for it?
Yes. So this is semantic entailment, which is kind of the same thing. It's very similar to the inference symbol, except it has got 2 bars instead of 1. Is that okay? So semantic entailment means everything that you can syntactically do makes sense. It is sound. Okay? But is that all we want? If this is all that we have, then what is the most extreme case of this is all we have, but the system itself is useless? I have no inference rules to be proven wrong. If I don't do a single thing, I cannot be doing something wrong. Does it still have syntactic entailment? Yes. Is it useful? Absolutely not. Okay, so are you guys convinced that semantic entailment by itself is not that useful? Because the empty set of inference rules, when zeta is empty, it means we have no inference rules whatsoever. Whatever you have in iota is all that you have. There's no way to spread the red, circling to anywhere else in that space. Does it have syntactic entailment? Does it have semantic entailment? Yes, because there's nothing in it. So when you ask the question, is every single inference rule making sense? I can say, absolutely, because there's no inference rule. Is that okay? So, you guys are still, some of you have worked already, and you understand what I mean by this. When you go to work, okay, and somebody else, and something went wrong, okay, let's say the server, for whatever reason, is not functioning correctly. And you say, okay, so whose fault is it? And then, person A stands up and go like, it's not my fault. I did not do a single thing today. You cannot fault me if I didn't do a single thing. Okay, so now we want to look at what about the other side of the coin, okay? So the other side of the coin is completeness. And completeness means that there's another entailment. Oh, that's the only one that I have. Dang it. Okay. So completeness means, everything that you can logically derive, okay, can also be derived by the syntactic system. And by the way, this one is not, this symbol means, pretty sure that's syntactic entailment. I'll look that up later. Okay. But the other way around is everything that you can prove to be true should be expressible by any number of steps in syntactic operations. Okay, let me say that one more time. Okay, it means completeness means if you can do it by hand, then the system should be able to do it as well using only the syntactic rules. That's the bottom line. Is that making any sense? But is completeness all by itself sufficient? Why not? Okay, if you can do, okay, so let's say you start with some iota, okay, and you say, okay, I can prove that theorem myself, and here's the conclusion. I can show why that particular well-formed formula is also true. Okay, so you can do it by hand. And then the system says, I can do it too. And you feed the same thing to the system, you feed the same iota, you give it all the inference rules, and it says, okay, I can come to the same conclusion. Well, that's okay. But what is missing in completeness? It only says that what you can prove, it can prove as well.
It doesn't mean that just because you can't prove it, the system can't prove it.
It can prove something that is not true to you.
Yeah.
Okay. For certain things, you can say, I cannot prove this. Okay, there's no way this can be a theorem because I cannot prove it. But the system says, I can prove it. I can show how that is true. So the system can be erroneous. Okay, even though everything that you can do, the system can do, but it can also do something that is wrong, that is not sound. That doesn't make sense. Is that making any sense to you guys?
So basically you can have an error in logic while you did the steps.
You can have certain syntactical rules, certain inferences that doesn't make sense. Okay, so it can lead to conclusions that you would not be able to reach because it doesn't make sense logically. So even though it has completeness, completeness by itself does not guarantee that everything is correct. Soundness, on the other hand, does not mean it can do everything that you can do. And you want both of these in order for the system to be helpful. Is that making any sense? Everything that you can do, the system can do, but no more.
So basically, you're saying that the same number of iotas you have, the system has to have as well. Something.
Say that one more time. Sorry.
If you have a certain number of iotas,
Mhm.
then the system has to have the exact same number, the exact identical. Right?
It's not about the iota. It's about how you label red in the space. Okay. So yeah, go ahead.
Oh no, I just remember I read something like a while back about like Gödel, and he made this thing called like Kurt Gödel, he's like this mathematician, and he made this thing called the incompleteness theorem, and it has something to do with like our arithmetic system. And I was just wondering if like this is like sort of the same thing. It's like saying that you can't have, it's not like it can't be consistent or sound and complete at the same time. Never mind. After.
The normal Boolean algebra system that we use is sound and also complete. But this applies to just any propositional logic system, because we are, from our perspective in this class, we are looking at propositional logic not really as the application of logic, but we look at it as the syntactic version or the very mechanical way of reasoning things. So the computer doesn't look at things the way that we do. It doesn't inherently understand what is a conjunction versus a disjunction. Conjunction is no more than just a symbol that is different from the symbol of conjunction. Disjunction and conjunction are just symbols to the computer. To us, they do have meanings, because we actually understand what is the meaning of and, the meaning of or, the meaning of not, and so on. So when we do reasoning, we are not really mechanically doing things. We are actually going by the meaning. But the computer doesn't understand the meaning, so it has to do everything by syntactic operations. In one way, you can look at a compiler, okay? So, when you want to specify how something is done, okay, you can just kind of hand write it in some way. If the other person can read it, it's just as good, right? But the computer cannot do that. The computer cannot understand your handwriting on a napkin. So what do you need to do? What do you need to do to have a computer to perform the same operations? Come on. You need to express it in a certain way. But what way are we talking about? In a particular language, right? And then whatever you express, it's going to be in a text file. It has to be processed syntactically by a compiler, and then the compiler cranks out some code, and that code is interpreted in return by the processor. So everything becomes extremely mechanical. When you say the word while in a loop, okay, in a C program, you know what a while means, right? Okay, while means as long as this condition is true, you'll keep doing this over and over and over again. Okay, so to you it has meaning. To the compiler, it is no more than just the ASCII code of W, the ASCII code of H, the ASCII code of I, and so on and so forth. It's just 5 ASCII code together. Okay, the compiler doesn't understand the word while, but it translates that into the code structure that implements what you understand a while means. Is that okay? So it's the same thing here, okay? Semantics, or what we can do with implication, is what you can write on a piece of napkin. Okay, all the reasoning, all the proofs they can do on a piece of napkin is this part here, is the implication. Because you're relying on the meaning of those operators to do the proof. But when you want a computer to do the same thing, you cannot just say, okay, here's a piece of napkin, solve this problem. It doesn't understand it, right? So you have to use syntactic operations, which goes to the inferences, the inference operations. Is that okay? Okay, so another way to look at this is going to be the last topic that we will talk about today, is you have a computer, and then you have a person, okay, and they're trying to do the same proof, okay. So you want the computer to solve every problem that a person can. You also want the computer to solve the problems correctly. Does that make any sense? So if you look at all the problems that this person can solve, okay, let's say that is a set like this. A system that is sound means nothing that the computer can prove is outside of this bubble. But what the computer can prove may be just a portion of what you can prove. It's a very small subset. Okay, this is sound, but not complete. Is that okay? On the other hand, if you represent the rules, or when you look at all the rules that you can use in Boolean algebra, and you translate it, but in the translation process, you introduce some errors. Okay, it is also possible that something that is not true, okay, which is out here, is the computer can prove those as well. So completeness is all it is doing is to make sure that whatever the computer can prove is a superset of what you can prove. But it may contain things that are not true as well. So certain things that is actually not true, like this spot here, to you, you would go like, I cannot prove that it's not a theorem. The computer, using the erroneous rules, but it is complete, will say that, yep, that's true. But everything that you can prove to be true inside the red circle, the computer can prove those as well. So that's why we need both. Okay, we need it to be sound, expanding the sound bubble all the way out to include the entire red circle. But we don't want anything outside of the red circle either, which means we look at completeness and we want to shrink that circle until it is just the red circle itself. So that's why we need both in order for a logic system to be useful. Now this perspective is definitely having a computer spin to it, because we are not talking about philosophy in this class. We're talking about how we can apply syntactic operations, inference rules, so that we can have computers to help us prove theorems. Okay? All right, so I'll give you a preview of what we'll be talking about on Wednesday so that you can read ahead of time. So you definitely need to understand what is resolution and how to transform an expression into conjunctive normal form in order to do your homework. But on top of that, what we also need to do on Wednesday is we'll be talking about proof by contradiction. Many of you have some exposure to proof by contradiction, but how do you prove that proof by contradiction makes sense? Where is the soundness of proof by contradiction? That is the question, okay? So this thing here, shows that. And on top of that, we'll combine all of those things, okay? So we'll combine the three things that we will have talked about on Wednesday: conjunctive normal form, resolution, and proof by contradiction, and go, oh, now we have a really easy system to solve or to prove theorems. The space of well-formed formula is finite. And we have a very systematic way to prove whether something is actually a theorem or not. We'll come to a conclusion either way. We'll come to the correct conclusion either way. Okay? So those are the things that we'll be talking about on Wednesday. Start working on the homework assignment. If you don't know how to proceed from a certain step, you can come ask on Wednesday during my office hour or in class. Okay. I'll see you guys on Wednesday. Unless you're also in my assembly class.